Welcome back to Carneades.org. Today we're going to be continuing with 6 months of set theory and higher order logic. In this video we're going to be checking out, is the null set a subset of all sets? And looking at a proof for that claim. So, now that we have an axiom officially introducing the null set, axiom 3, we're going to prove some properties of the null set. That's what this whole first month is about. It's about properties of sets. In this video, we're going to formally prove a claim that we mentioned in a previous video. That's the claim that the null set is a subset of all classes. We mentioned this in a previous video on swelled sets because swelled sets always have to have the null set in them because the null set is a subset of all classes. Check out that video to see why, but for now, we're going to take a look at why that claim is true, because we kind of offered it with a bit of a general informal proof, but now we'll do a line-by-line more formal one. Hopefully this is going to provide some insight into how to actually use the formal definitions of these various axioms. So, in other words, the goal is to prove the following statement. For all A, the null set is a subclass of A. Or in other words, the null set is a subset of all classes. I highly encourage you to try this on your own if you want to practice your logic skills and get better at manipulating set theory notation. This one is easier than some of the other long proofs that we've done, so I recommend giving this one a try if you haven't tried one yet. But with that, let's get going. So we're going to look at our conclusion needs to be for all A. The null set is a subclass of all A. As you can see by the line going down, we're going to start with an indirect proof. So we'll do an indirect proof denying that, saying it's not the case that for all A, the null set is a subclass of all A. Change of quantifier gets us that there exists an A such that it's not the case that the null set is a subclass of A. We'll existentially instantiate F in for A. And then we're going to use our subclass definition rule. Remember, we can just sub in using identity and any definition when they are equal by definition to get, it's not the case that for all A, X is a member of the null set implies that X is a member of F. Once again, use our change of quantifier rule to get that negation inside the quantifier. Use existential instantiation to instantiate X to G. We've got, it's not the case that G is a member of the null set implies that G is a member of F. We use implication to change that implication sign into a disjunction and a negation. And then De Morgan's rule and double negation to get G is a member of the null set and it's not the case that G is a member of F. Well, it's not the case that G is a member of F doesn't tell us much, but G is a member of the null set is going to be problematic. That's going to go up against our definition of the null set. So we'll simplify that out. Then we'll look at our definition of the null set for all B. B is not a member of the null set. And by universal instantiation, we can instantiate that B to the G that we have and say G is not a member of the null set. And our non-membership definition gets us the formal negation of G being a member of the null set. We can join that with premise 9, and we've got it's not the case that G is a member of the null set, and G is a member of the null set. Therefore, we have a contradiction, and by 1 through 13, indirect proof, we can say that for all A, the null set is a subclass of A. Up next, we're going to look at, is the null set supercomplete, and do another line-by-line proof. I'd encourage you to try that one on your own right now. Watch this video and more here at Carneades.org, and stay skeptical, everybody.